Hi, ladies and gentlemen. We are looking at notes 2.2, which are in the middle of page 4. And we're going to be talking about theoretical probability now. Before we talked about experimental probability, now we're going to talk about theoretical probability. So here it says theoretical probability is another measure of the likelihood of an event. Without performing experiments, so no experiments this time, theoretical probability measures predicted outcomes or expected outcomes. Okay, you don't have to write this down, but I do want you to hear what I'm going to say next. So, for example, let's say you toss a coin 20 times and you get heads 12 times. Okay, so the difference between experimental probability and theoretical probability is as follows. So the probability of getting heads based on your experiment is 12, because you have 12 successful tries out of 20, and then when you simplify that, they're both divisible by 4, so divide them both by 4, and you end up getting 3 out of 5, okay? But the probability of getting heads in theory, there's only one way, there's only two options when you flip a coin. You can either get heads or you can get tails, and that's the difference between the two. So since there are two outcomes right here, one is what we want, so it's 1 out of 2. So the theoretical probability is 1 out of 2, but the experimental probability is 3 out of 5, okay? So the theoretical probability formula is still going to be the same idea. So the probability of an event is still going to be equal to the number of successful trials over the total number of trials. Okay? So to calculate theoretical probability, all outcomes must be equally likely. Meaning each event has the same chance of occurring because the conditions are fair. So if you have a fair coin, for example, the likelihood of getting a heads is the same as the likelihood of getting a tails. If you have a fair die, for example, the likelihood of getting a 4 is the same likelihood as getting a 6, okay? And then don't forget that the probability of an event is a value between 0 and 1. And let's just remind ourselves that 0 means it's never going to happen, so not possible. And then 1 means it's definitely going to happen. This is going to be certain. Okay? So take a look at the next page. It says, suppose you were to flip a coin 3 times. Use a tree diagram to help determine the possible outcomes. Well, we did that, but that was an experiment. So now we're going to talk about the different possible outcomes theoretically that you should get. Okay? So a tree diagram is just going to diagram all different possibilities. So the first time you flip a coin, so we'll have coin number 1, you have two options. You can either get heads or you can get tails, okay? Then you flip a coin a second time. So for coin 2, you have two options, but it's off of the possibilities for coin 1. So for example, right here, if I got heads the first time, the second time I flip a coin, I still can get either heads or tails. So this means that if I got heads the first time, then I could get heads followed by heads, or I could get heads followed by tails, okay? And then this one right here is saying if I got tails the first time, if I flip a second coin, I've got two options. I can either get heads or tails. So I could get tails followed by heads or tails followed by tails, okay? And then I've got coin number 3. And coin number 3, off of each one of these, I have two options. So I can either get heads or tails off of each one of these options right here. So heads or tails for all of these, okay? So what ends up happening is I end up getting 8 different outcomes. And I know that because the last part of my tree diagram has 1, 2, 3, 4, 5, 6, 7, 8 outcomes. So here I'm going to write down that I have 8 outcomes, and then I'm going to list out what my 8 outcomes are. So my 8 outcomes are going to be as follows. The first one would be I got heads first, heads second, and then heads third. So I could get heads, heads, heads. Okay? My second outcome is saying that I could get heads first, heads second, but then tails third right here. So I could get heads, heads, tails. Okay? My third option, so I'm done with this first option that leads us to this last H right here. I'm done with the second option that leads us to this last T right here. My third option is I could get heads first, heads second. Nope, I'm sorry. I'm also done with my heads as well. So I could get heads first, tails second, and then heads third. So I could get heads, tails, heads. So that's my third option right here. My fourth option is I could get heads first, tails second, and then tails third. So I could get heads, tails, tails. So that's my fourth option. And now I finished all the first 4 options, which means I'm done with getting heads first. Okay, so now I'm going to look and see what happens if I get tails first. So if I get tails first, I'm going to follow the path. I could get heads second, and then I could get heads third. So I'm done with that option. So I've got tails, heads, tails. The sixth option right here is I could get tails first, heads second, and tails third. So right here I could get tails, heads, and tails. And I apologize right here. This should be tails, heads, heads, because it goes tails, heads, heads up here. Okay, so I'm done with my sixth option. My seventh option, I could start with tails, and then it brings me over to tails now, and then it brings me up to heads. So this is going to be tails, tails, heads. And then my last and final option is I could start with tails, go to tails, and then end with tails. So I've got tails, tails, tails. Okay. Now, if you remember when we did our coin flipping experiment, event A earning 3 points happened if we got 3 tails. Okay, so if we got 3 tails, that's outcome number 8, because outcome number 8 says we get tails, tails, tails. All of the other outcomes have at least 1 heads in it. So this is outcome number 8. If you remember, event B was earning 1 point, and event B was if you ended up getting 2 tails. So I'm going to look through my list and find all of the possibilities that have 2 tails. This has no tails. This has 1 tail. This has 1 tail. This has 2 tails. This has no tail, or just 1 tail. This has 2 tails, and this has 2 tails. So right here, the event B is outcome number 4, number 6, and number 7. Event C, if you remember, ended up happening if we had either 1 tail or 0 tails. Okay, so for this right here, we're going to go through our checklist and see which ones have either 1 tail or 0 tails. This had no tails, so that works. This has only 1 tail. This has 1 tail. This has 2, so that doesn't work. This has 1, this has 2, this has 2, this has 3. So the outcomes that would give us 0 tails were outcomes number 1, number 2, number 3, and number 5. And here we had 8 outcomes, and all 8 outcomes are covered. Okay, so listing the outcomes in the events gives us a clearer indication of the chances of having a particular event occur. In this case, you can calculate the theoretical probability for each of the events. So these probabilities are going to be different than the actual probabilities you got when we did the experiment. And every group got different answers, but when we do the theoretical probability, every single person will always get the same answer because it's the predicted probability. So right here, the probability for event A, in order to find the probability for event A, let me do this in purple since I did it in purple up here. The probability for event A, I'm going to look for the number of successful outcomes over the total number of possible outcomes. So to find the probability of A right here, we know that there was one successful outcome, and it was outcome number 8. So that's the number of successes, and we know that there were 8 possible outcomes, so it's 1 out of 8. Okay, so we can say it's 1 out of 8, and then we can figure out what it is as a decimal. So I'm going to take 1 and just divide it by 8, and I get 0.125. So the probability of A is also written as 0.125. And as a percentage, we just move the decimal place over twice, so that's 12.5%. Okay? All right, so now the probability of event B, same thing, it's the number of successes over the number of possibilities. So we had 3 successes because we had 1, 2, 3 outcomes that worked out of 8 outcomes that we had all together. So I'm going to calculate what 3 divided by 8 is. So 3 divided by 8 gives me 0.375. So the probability of B is 0.375. And as a percentage, the probability of B, remember you just move this over twice, is 37.5%. Okay? And then the last thing that we're going to do is the probability for event C. So the probability of C, we had 1, 2, 3, 4 successful outcomes out of 8, but 4 and 8 have a number that they have in common that I can divide them both by. They're both divisible by 4, so I get 1 out of 2. So the probability of C is just 1/2, and 1/2 as a decimal is 0.5, and half as a percentage is 50%. And altogether, all of these percentages should add up to 100%, which they do. So this is what we should have expected for our probabilities, but it's not exactly what happened when we did this. So we're going to talk about why that didn't happen in class, okay? All right, so now let's go ahead and do our example right here. So example number 1 says a standard deck of playing cards has 52 cards, 13 of each suit. So just a reminder, in case you're not sure, in a standard deck of cards, you have 13 spades, and pardon my drawing, I'm not the greatest of drawers, but this is supposed to be spades, okay? You have 13 clubs, which are the ones that look like clovers, okay? And those are black cards, okay? And then you also have half of the cards are red. So we have 13 hearts, which are red, and we also have 13 diamonds, which are also red, okay? So if one card is drawn from the deck, find the probability of each event. So if I want to find the probability of getting a heart right here, so I'm going to say the probability of getting a heart, I'm going to look for the number of hearts over the total number of cards. Okay, so right here, we know that there are 13 hearts, and we know that there are 52 cards right here. So 13 over 52 right here is going to be my probability. But 13 and 52 are both divisible by 13, so you end up getting 1/4. So the probability of hearts is going to be equal to 1/4, which is 0.25. If I were to divide it, if I were to divide 1 divided by 4, I should get 0.25. You should also know that a quarter is 25 cents, so you don't need a calculator for that, which is 25% right here. So that's the probability of getting hearts, okay? The probability of getting an ace, if you remember right here, in your cards, you have one of each card in each suit. So there's like a 2 of spades, a 2 of clubs, a 2 of hearts, a 2 of diamonds, so there's 4 2s altogether. So since we're looking for the probability of an ace, we're going to look and see there's an ace of spades, an ace of clubs, an ace of hearts, and an ace of diamonds. So to find this answer, we're just going to say to find the probability of ace, it's the number of aces over number of cards. And I guess I don't need an apostrophe here. So there are 4 aces out of 52 cards. They're both divisible by 4, so I end up getting that the probability is 1 out of 13. Okay? All right, so now this right here, the probability of a heart, a club, or a jack is a little bit trickier, so make sure you're paying really close attention to this. So we're going to look for the number of hearts and the number of clubs and the number of jacks all over the total number. But I want you guys to write yourselves a note right here that the number of jacks right here, there are 2 jacks that are already counted. There's the jack of hearts and there's also the jack of clubs. So we have 4 jacks altogether, but 2 of them already counted here. So there are only 2 extra jacks in addition to the jacks that are here. So we need to avoid any repeats. Okay, that's really important that you understand that you avoid those repeats. So right here, the probability of hearts, clubs, or jacks, we know that there are 13 hearts, including a jack. We know that there are 13 clubs, including a jack, and that there are 2 more jacks in addition to the jack of hearts and the jack of clubs, all over 52 cards altogether. So 13 plus 13 is 26, plus 2 is 28. So you get 28 out of 52. 28 and 52 are both divisible by 4, so you end up getting 7 out of 13. So the probability of this is 7 out of 13. Okay? All right, and then lastly, question D says find the probability of a heart, a club, a spade, or a diamond. So to find this, we need the total number of hearts, which are 13, the total number of clubs, which are also 13, the total number of spades, which are also 13, and the total number of diamonds, which is also 13. Nothing is going to be repeating because there's no way a card could be a heart and a club at the same time, for example. All over 52 cards altogether. So if I add 13 plus 13 plus 13 plus 13, I get 52 over 52, which is 1, which means that there is 100% certainty that a card is either going to be a heart, a club, a spade, or a diamond. And that should make sense to you because when I take a card out, it's going to be one of those 4 things. It's not going to be anything other than a heart, a club, a spade, or a diamond. Okay? All right. Example number 2, it says Cody rolls a regular 6-sided die. Find the theoretical probability of each event. Express your answer as a fraction in lowest terms and as a percent. So right here, to find the probability of rolling a 6, I'm going to find the number of 6s. And remember, this is theoretical, so it's not based on an experiment. It's just what we would expect. So the number of 6s over the total number of sides. And in a die, you only have 1 6, and there are 6 sides. So the probability is 1 over 6. That's in lowest terms. I can't simplify that anymore. As a percent, I'm going to take 1, divide that by 6, and I end up getting about 17%. So we can say that this right here, the probability is 17%. Okay? Question B says find the probability of rolling a number greater than 2. So we're going to say the probability of getting a number greater than 2. So let's list out all the numbers greater than 2 that we could get on a 6-sided die. So we could get a 3, a 4, a 5, or a 6. So that means that there are 4 outcomes out of 6 that work for us. Both of these numbers are divisible by 2, so you end up getting 2 over 3. Okay, so right here, that's my answer. Now I'm going to divide 2 divided by 3, and I end up getting 0.6 repeating, which is about 67%. So the probability of getting greater than 2 as a percentage is about 67%. Okay? All right, now part C, find the probability of rolling an 8. So we'll say probability of rolling an 8. So we're going to do the number of 8s over number of sides. Well, on a 6-sided die, there are 0 8s over 6 sides, so the probability of rolling an 8 is 0. 0 divided by 6 is 0. So the probability of 8 as a percentage is 0%. Okay? And then lastly, we have the probability of getting an even number. So we want to find the probability of an even number. So on a die, we've got options 1 through 6. Our even numbers are 2, 4, and 6. So we have 3 options out of 6 sides. So this right here, when I reduce this, it's 1/2. And then as a percentage, that's 50%. So the probability of getting an even is 50%. And that's how we do theoretical probability. This is the first day of 2 days of theoretical probability. We're going to get more into detail next time you guys watch the video, but this is it for now. All right, have a good day.